In this video, we will discuss a few solved problems on capacitors. These include capacitance calculation based on geometry of a particular capacitor, calculation of equivalent capacitance for a network of capacitors, followed by energy density calculations associated with electric fields that exist between the plates of capacitors. Problem 1. An air-filled spherical capacitor is constructed with inner and outer shell radius of 7 and 14 cm respectively. So that means the inner sphere has a radius of 7 cm and the outer sphere has a radius of 14 cm. First, calculate the capacitance of the device and also the potential difference between the spheres if there is a charge of 4 microcoulomb on the capacitor. So let's do part A. Now this is a spherical capacitor and the region between is filled with air. So to a good approximation, we can assume it's pretty much empty space. So the permittivity can be taken to be epsilon naught, the permittivity of vacuum. The expression for the capacitance of a spherical capacitor is given in one of our previous videos in capacitor, and that is quite simply 4 pi epsilon naught, the product of inner radius and the outer radius over the outer radius minus the inner radius. So substituting the information that we have inside this equation, we have 4 pi epsilon naught is permittivity of a vacuum, so 8.85 times 10 to the power minus 12 in SI units. The inner radius is 7 centimeters, so it's 0.07 meter. The outer radius is 14 centimeters, so it's 0.14 meter. Divide by the difference in outer and inner radius, and that is 14 minus 7, so that is 7 cm or 0.07 meter. So these two terms cancel, and the entire term will give you an answer of 1.56 times 10 to the power minus 11 farad. It's in SI units. Part B. What is the potential difference between the spheres if you have this much charge on the capacitor? So let's assume that the inner sphere carries a positive 4 microcoulomb and the outer sphere carries a minus 4 microcoulomb. So that is your Q. Now to determine the potential difference, we can use the formula that we are familiar with. Charge equals capacitance times the potential difference. Now since we know what the charge is, it's 4 microcoulomb. So micro is 10 to the power minus 6. Capacitance we have already calculated from part A, 1.56 times 10 to the power minus 11 farad times the potential difference. And you can get what the potential difference is. And it turns out to be 2.56 times 10 to the power 5 volts. And that solves the problem. Problem 2. A parallel plate capacitor is constructed using a dielectric material whose dielectric constant is 3. And the dielectric strength is 2 times 10 to the power 8 volts per meter. The desired capacitance is 0.5 microfarad, and the capacitor must withstand a maximum potential difference of 4,000 volts. Find the area of the capacitor plates. Now, as you will see, this area corresponds to the minimum area the capacitor can have. So let's assume you have such a parallel plate capacitor, and the area is a meter squared, and this is the minimum area for the conditions imposed by this problem. And what is that minimum area? Now note that we are given a dielectric strength of 2 times 10 to the power 8 volt per meter. Now what that is based on the units, is quite simply the maximum electric field that can be placed in the region in between these two parallel plates. Any attempt to make the electric field greater then that maximum electric field, or what we call the dielectric strength of this material that fill up the region in between, will quite simply burn that dielectric material. Now we know that the electric field between such a parallel plate capacitor is given by the surface charge density sigma over the dielectric constant, which we know to be 3, times the permittivity of vacuum. Together, they're going to give you the permittivity of that dielectric material. And we can write the surface charge density as charge over that area of that plate, of this parallel plate capacitor. Since this is a maximum electric field expression, the charge must correspondingly be maximum and the area must be minimum in order to make this electric field maximum. Now, since we are told that the desired capacitance is 0.5 microfarad and the capacitor must withstand a maximum potential difference of 4000 volts, so when the potential difference is 4000, the charge must be the maximum charge. So the capacitor equation will look like this. This maximum charge can be calculated as follows. So the capacitance is 0.5 microfarad and the potential difference, the maximum potential difference, is 4000 volts, and that's going to give you 2 times 10 to the power minus 3 coulomb for this maximum charge. So since we know the maximum charge, we know the maximum electric field, which is just the dielectric strength of the material. We know the dielectric constant of the material, permittivity of vacuum. We can use this equation to figure out the minimum area of that capacitor plates. Substituting these numbers, we get 2 times 10 to the power 8 for the maximum electric field, 2 times 10 to the power minus 3 for the maximum charge, as we have computed here, divided by the dielectric constant is 3. The permittivity of vacuum is 8.85 times 10 to the power minus 12 times the minimum area. And solving for the minimum area, we will get the minimum area to be 0.377 meters squared, and that solves the problem. Problem 3. 4 capacitors are connected as shown in figure below. Find the equivalent capacitance between points A and B for this capacitor network. So this problem needs to be done in stages. First, let's combine these two capacitors, the 15 microfarad and 3 microfarad capacitors. These two capacitors are in series. So these two capacitors can be combined in a following manner. Let's say the resulting capacitance is C15.3. So that is 1 over 15 plus 1 over 3, which is 6 over 15. That means the result of combining these two capacitors will give you a new capacitor with a capacitance of 15 over 6 microfarad. And since we have already combined these two capacitors, we can redraw the diagram in a following manner. Like that. And of course, this is point B, this is point A, and now the top capacitor has a capacitance of 15 over 6 microfarad, and this is still 10 microfarad, and this is 6 microfarad. The next step is to combine these two capacitors. Now they are in parallel. So let's say the result of combining that two capacitors will result in a capacitor with capacitance, say, 15.36. And the result for that capacitance is just 6 plus 15 over 6, because that's how we combine two capacitors in parallel. And this will give you 8.5 microfarad. Basically what we have done, we have reduced further the above circuit to a much simpler circuit involving just two capacitors. Like that. This is point A and this is point B. The right capacitor is 10 microfarad capacitor, so that is that one. And this capacitor is the capacitor that results by combining the first three capacitors. That is this, this, and that. Finally, we can combine these two. These two capacitors are in series, and let's call that capacitance as C equivalent. So 1 over C equivalent is quite simply 1 over 10 plus 1 over 8.5. So that's how you combine two capacitors in series. And solving for that equivalent capacitance will give you 4.59 microfarad as the final answer to this problem. Problem 4. A uniform electric field with a magnitude of 3000 volt per meter exists within a certain region. What volume of empty space contains an energy equal to 1 times 10 to the power minus 7 joules? Now, before we have talked about the expression for energy density associated with a electric field, and that is given by the following expression. U subscript E is half permittivity of vacuum, because this is an empty space, times the square of the magnitude of the electric field. Now note that this is energy density. That means it is energy over volume, and with a unit of joules per cubic meter. What we are interested in here is that we can calculate the entire ratio, and we are given this number, and we are supposed to determine the volume. So let's first determine the energy density. It is half times the permittivity of vacuum, 8.85 times 10 to the power minus 12. The electric field is 3000 volt per meter, so square that. And that is supposed to be U over V, and we know what U is. It is 1 times 10 to the power minus 7 joules divided by V, the volume. So solving for V, the volume, we will get 2.51 times 10 to the power minus 3 cubic meter. So this much energy density implies this much energy is contained within this much volume. That solves the problem. Problem 5. An 10 microfarad parallel plate capacitor has a plate separation of 5 mm and is charged to a potential difference of 400 volts. Find the energy density in the region between the plates. So note that, so you have a couple of plates like that. The separation distance is of 5 millimeters, and you have a potential difference of 400 volts in between the plates. Now that means the electric field between the plates would be 400 divided by 5 millimeters converted into meter, 0.005. And this electric field is in the unit of volt per meter. Now the energy density that you are interested in can be calculated using the usual formula. Half permittivity of vacuum, so we are assuming the region in between is occupied by vacuum, times the square of the strength of the electric field that we have computed above. So substituting the numbers, half 8.85 times 10 to the power minus 12 for permittivity of vacuum, times 400 over 0.005, do not forget to square it, and you will get the energy density in the region between the plates, and that will turn out to be 0.028 joules per cubic meter. And that solves the problem. Thank you for watching.